Hello and welcome to a tutorial in CS 3002. In this tutorial, we are going to be familiar with an example using method of fragments. I know that there are several alternatives which may be more complicated, but the accuracy is not that much. So therefore, I choose method of fragments as an example for you to understand the concept. You know that nowadays engineers will use software to calculate seepage because it is more accurate. However, if you don't understand the concept, it may be hard to interpret the result from the software. Now, let's start with the exam in 2022. Alright. So, you must use the method of fragments to calculate the seepage underneath the dam given the hydraulic conductivity K equal to 1.5 10 minus 6. To use the method of fragment, in the first step, you need to divide your foundation into fragments. And the tip to divide it is that when it has a change of the depth of the soil layer, it's a new fragment. So for example, in here, you have a step from the concrete apron that is about 1 meter. So therefore, there must be a chain of fragment. So this one must be the boundary between two fragments. Here will be the fragment 1, and next one will be fragment 2 until the change of the depth. You can see we have the step over here, so therefore this is a change of fragment. And here's the next one, and next one. Now, please pay attention here. In here, we have the change of material from concrete to free surface. However, there is no change of the depth. So, therefore, there still be the same fragment. So, this one is next one, and the last one. Alright. Now, the second step, after you have divided the foundation into fragments, you need to identify the type of the fragment. Let's see what are they. The first one, we have free surface and a step. So therefore, we need to look at the table with the form factor to find what is this. Alright, free surface and a step. So it must be this one. You have free surface and a step. You can see that. So it must be of type 2. In the next one, you have an impervious apron on the top and a step over here. So just have a look. Impervious on the top and a step should be this one. Please do not choose this one because in here you have the free surface over here, so it shouldn't be type 3, it must be type 4. Alright, so this one must be a type 4. For this one, it's quite easy because it has only one impervious top and no step. So therefore, when we look in this one, we find this one must be type 1. Alright, so this one must be of type 1. And the same to this one. Now for this one, we have the impervious top and 2 steps with the equal length on the side. So therefore, when you look at the table of form factor, you can see that it should be of type 5. Alright. So this will be of type 5. And the last one, you have the impervious top with free surface and the step over here. So therefore, if you look over here, you will see that the free surface, impervious top, and the step. So it must be of type 3. So this one must be of type 3. So 1, 2, 3, 4, 5, 6 fragments. They quite a lot, but we can overcome it. So for fragment number 1, it should be this one and type 2. Alright, so I need to calculate the m number first. My m equal to sine of pi times by s over 2t, where t is the thickness of the soil layer, is equal to sine of pi times by the step, which is 1, over 2 times by the thickness should be 25, because I have just one small step over here, so should be 25. And I have this number equal to 0.06279. From here, I must get the number m squared, which equal to 0.0033943. In general, I often have about 4 significant digits because I want to have the accuracy of 1%. So when it accumulated the error, it's still less than 1%. And from here, I look at the table. Alright. Now, let's have a look at the table. I think I have it somewhere over here. So, I have my m squared equal to 0.03. So, it must be in between this one. And I look for the value of k on k dash should be this one. So, I use interpolation to find the number of this one, and it must be roughly my phi 1 is to avoid the confusion, I should use this number 1, because otherwise you will be confused with the type of the fragment. So phi 1 for the fragment 1 equal to 0.378. Alright. Now for fragment 2, I have it of type 4. So I have to consider the condition of S, which is a step, and L, which is a length. I have S equal to 4 and it is smaller than 29, which is equal to L. So therefore, in this one, I have to use these equations because my S is smaller than L. Alright. So from here, I have my phi 2 equal to natural logarithm of 1 plus s over t minus s plus l minus s over t. Alright, where it should be the natural logarithm of 1 plus the step, which is 4. This is a step. Alright, over the t minus s. Now please remember that now our t, the depth has changed. It doesn't have the 1 anymore because the depth of the layer now is 1 meter smaller. So it should be, t should be 24 and minus s should be 4 plus l, which is 29. You have it from here. Alright, minus s, which is 4, over t again, which is 24. Alright, so this one I have, it should be about 1.224. Now for fragment 3, alright, I have it is of type 1, so it's quite easy for me. From here, I have my phi 3 equal to L on T, which is 6 meter length over the depth. Now should be just only 20. So it should be 0.3. And it equal to 5 for the fragment number 5, because they have the same length and the same depth and the same type. Alright, for fragment 4, I have it is of type 5. Now I need to consider the conditions. So I have my length, which is equal to 18 meter. Alright, and it is larger than 2s, which is 10. So from here, I can calculate my phi by the equations. In here, I have my L is larger than 2s, so I must use these equations. Alright. So my phi equal to 2 natural logarithm of 1 plus s over t minus s plus L minus 2s on t, which is 2 natural logs of 1 plus the step, which is 5, over t minus s should be, now please be aware that the t has changed as well, so now the t will be this one, which is should be 25. Alright, it's not 24, it's 25, so it should be 25 minus 5 plus L, which is 18, minus 2s should be minus 10 over t, which is 25 now. So I have this one should be about 0.766 and 3 if you want the fourth number. Alright, for the last one, fragment 5 we already calculated together with fragment 3. For the last one, which is a fragment 6, I have it is of type 3. I have to calculate the parameter m. My m for type 3 equal to cosine of pi times by the step over 2 times of the thickness times by the square root of tan h. It's not the normal tan, it's a tan h, the hyperbolic tan, of pi times by b, which is the width of the impervious top, over 2t, which is the thickness of the soil layer, plus tan square, now it's a normal tan, of pi times by s over 2t. Alright, so I submit my number into this one. It's equal to cosine of pi times by S. I have my S here is 5. Let me double check it. Yes, because this one is 4 plus 1, so therefore this one must be 5. Alright, because this one and this one and this one have the same level, so therefore this one must be 5. The step must be 5 over 2 times by the thickness. The thickness now should be the full thickness, should be 25, times by square root of hyperbolic tangent of pi times by b. My b which be the length of the impervious top, which is 21. Let me double check. Yes, it is 21 over 2 times by 25 plus tan square of pi times by 5 over 2 times by 25, and you can get this number is 0.8803. From here I can have my value of m square, which is equal to 0.7749. Yep, and I use the table again to get my value 56 equal to, let me check it, 0.7749. So you can see here the m square and at 0.50, so therefore I have to use this column to go up, so 0.7749 should be in between this one, and I go from this one to this value of k over k dash. Now please remember that if you use the left column, you must use the heading on the top here. Alright, but if you use the right column, so you must use the heading at the bottom. Alright, so now from here I can get it in between 1.31 and 1.33, and I can use interpolation to find the value of this one, which is about 1.32. Alright, now I have all of the value and I can apply the general equations of method of fragment. So I have the discharge Q equal to K times by sum of delta H, which is the difference of the water level from the upstream to the downstream, over sum of phi. Alright, so in here I have from the given data is 1.5 10 minus 6 meter per second, 10 minus 6 meter per second, times by sum of the difference. So I have a look over here, so groundwater level is right here and the upstream is right here, so the difference is 27 times by 27 over phi 1 plus phi 2 plus phi 3 plus phi 4 plus phi 5 plus phi 6, which is 0.378 plus 1.224 plus 0.3 plus 0.7663 plus 0.3 plus 1.32. Alright, so this is 5.1, this is 5.2, this is 5.3, this is 5.4, this is 5.5, which is equal to 5.3, and this is 5.6. All of this we just calculated, and from here I have my discharge of the seepage underneath equal to 9.5 44 10 minus 5 meters square per second. The reason why it is meter square per second is because we are calculating for 1 meter length of the dam. So therefore, if you times by 1 meter length, you will need cubic meter per second. Alright, so that is the first question. Now, let's move to the second question. In here, you need to calculate the head loss in each fragment and the total uplift force acting on the dam only. I'm going to do this a bit down here. So for the part B, I can use the equations for the head loss. My delta H, alright, will equal to 5 times by the sum of delta H over the sum of 5. And I apply for every single fragment. So for fragment 1, I have my delta H1, the head loss in this one, equal to phi 1 times by sum of delta H over sum of phi. And this is a constant, so I can do it for all of the others. Alright, my delta H over sum of 5, which is 6.296. Yeah. This value will be this one. Alright. So from here, I will have is equal to 0.378 times by 6.296, and this one should be 2.38 meter. My delta H2 equal to phi 2 times by 6.296. Alright, it will be 1.224 times by 6.296, and this one is 7.707 meter. Now my delta H3, which is equal to delta H5, equal to phi 3 times by 6.296, which is 0.3 times by 6.296, and this is equal to 1.889 meter. Delta H4 equal to phi 4 times by 6.296 equal to 0.7663, and it should be about 4.825 meter. My last one, delta H6 equal to phi 6 times by 6.296, and is equal to 1.32 times by 6.296 equal to 8.311 meter. And when you sum up all of this one, please don't forget to times this one by 2, because you have delta H3 and delta H5. When you sum up all of them, you can see that it equal to 27. So that means it's okay. You didn't do any mistake. That's a cross check if you do any miscalculations. And in the next step, we need to calculate the total uplift force acting on the dam only. So we only focus on this dam. because there's maybe a connection right here and a connection right here, so therefore the uplift force here may be not transferred to the upstream and downstream. So we want to see the uplift force right for these three fragments. All right, so now I need to do the point. So I have will be my first one, something like this, which will be my point A, then my point B, and then point C, and then point D. And I will calculate the pore pressure at each point, and then I will add up to get the diagram of the uplift force. All right. Now my HSA is equal to H, which is the upstream level. Then I have to minus the water loss before that the fragment. Alright, so I have to minus delta H1 minus delta H2, and I have it equal to 27 minus 2.380 minus 7.707, and it is 16.91 meter. Alright, now at HB I have it equal to HA minus the head loss in this fragment should be delta H3. So I have this one equal to 16.91 minus 1.889, and it is 15.02 meter. For the HC, I have this one will be HB minus the head loss, which be delta H4. I have this one should be equal to 15.02 minus 4.825, and this is 10.02, 10.20 centimeters, sorry, 10.20 meter. And the last one, the HD, all right, is equal to the HC minus the delta H5, which is equal to delta H3. It is 10.20 minus 1.889, and it is 8.311 meter. Alright, so now for understanding I can draw this one for you. In the first step, water flow from the reservoir into the ground, and it lose some energy in this fragment, the fragment 2. Alright, so it's going to have something like this, and this will be the delta H1. The gap over here should be the delta H1. Alright, after the fragment 2, which is of type 4, we have is lose the delta H2. So this one will be your delta H2. Now I change the color so we can see clearly. So this will be the value of HA. Alright. Now after that, we have to reduce the water head by H3, delta H3, to get to the new level. So this will be your HB. And keep going on. We reduce this after this one to get the value of HC. And after that, we have to reduce it to get the value of HD, something like this. And at the last one, you going to match up with the groundwater level. Alright, please remember that all of the H based on the same datum, which is this datum, the datum at the upstream and downstream side. Alright, if you use this as a datum, you have to be consistent with that. You also can use this one as a datum, but it makes your calculation more complicated. Right, so I recommend to take this one as a datum. You reduce the delta H. So this one should be delta H3. This one will be delta H4. And this one should be delta H5. Now the uplift force going to be the one that underneath the water head. So when you see that it acts on this one, you're going to have the uplift force will be this diagram. Alright, the uplift force will come from the foundation, the plane that you act on, not from the datum, because it acts on this one. Alright, so this will be the full one. You need to add up 5 meters because you are under the datum 5 meters. For this one, it will be this part because you act right over here. For this one, you have to act on this one, so therefore your uplift force will be this one again. Alright, so you have 3 trapeziums and the formula will be like this. If you forget, the formula for trapezium will be the area will be equal to A plus B over 2 times by H, where A and B is the length of the bottom and the top, and the H is the height. Alright, so we apply it for the 3 trapezium. We will have the sum of the uplift force will equal to the gamma of water, because we need to calculate the force, not the density, time by, for the first one, it should be this value 16.91 plus 5, because this is the depth under the datum. Under the datum. Alright, this is the A plus B, you will have 1502 plus 5. It's under the datum over 2 times by the height, which is 6 meters, plus 1502 plus 10.20, which is this value, over 2 times by the height, which is the length of the fragment, which is 18, plus, now let's go a bit over, 10.20 plus 5. Alright, this is the depth under the datum. Plus 8.311 plus 5 over 2 and times by the height, which is 6. Alright, and all of this give me the value of the uplift force, which is 4.30 10 power 6 Newton per meter. The reason why we have per meter here is because we are calculating for 1 meter length of the dam. If you time up by 1 meter length, you will have the force in Newton, so about 4.3 mega Newton. Now, for the last questions, we need to find the existing gradient at the downstream side. Given the hydraulic gradient IC equal to 1.2, is the dam safe from backward erosion or not? So we need to find it with the table, with the equations, or with the value from the table. I think I can do either way, but I prefer to do with equation because it's more accurate. Now, existing gradient at fragment 6. I have my m square equal to 0.7749. So from here, I get my k factor equal to 2.2. Alright, from the table. And from here, I have my existing gradient IE equal to delta H times by pi over 2k t m. So I have this one should be 8.311 times by pi over 2 times by k, which is 2.2, times by t, which is the thickness, is 25 meter, and times by m, which we calculated before, which is 0.8803. So from here I can have my existing gradient is 0.27. Now you can see that my critical gradient IC equal to 1.2, right? Let me double check. 1.2. Yep. My existing critical gradient equal to 1.2, and it's larger than 3 times of the existing gradient 0.81. Yeah, so from here it is safe. Now let's compare the calculation we have just done with the result from a software. In this example, I take Geostudio Seep. So here is the geometry I have drawn and the calculation of seepage. Now I just want to see the uplift force only. So first of all, I want to see the distribution. So I click on graph and try to add a new one. And I use is maybe water pressure head because I calculate in meter. Yeah, and versus X, and then I set locations. I select this geometry and this geometry and this geometry. Please select the bottom, not the top, and then show graph. So here you can see this is my first trapezium, this is my second trapezium, and this is my third trapezium. The add up here because of the gap over here. Alright, now just compare the value. So on the top I have it 21.84, and in my calculation I have this one should be 16.91 plus 5, which is 21.91, so very close. So for this point A, I have the water head quite close. For the next one, the gap should be bigger. I have here 19.09, but in my calculation I have is 15.02 plus 5, which is should be about 20.02, so about 1 meter gap. This one is 13.27, and in my calculation I have this one is 15.2, so now the gap is even bigger, it's about 2 meter. The main reason is because you can see here, in here we still have the water head loss, but in the method of fragment we assume that there is no water head loss in this vertical interval. We move from this fragment directly to this fragment. So therefore I think method of fragments is approximate but not accurate as the computer solutions. But the value is close enough, we can see later, right? So for this one, we will have is 11.15 and so on. Now, if I want to see the total of the uplift force, I try to make this one against the time, and I sum up all of the y value. So I have this one about 472 water head, and if I times by the gamma of water, which is about roughly 9.81 kilonewton per meter, so I will have is roughly about 4.5, I think so, 4.5 meganewton. So it's very close to the one I calculated before, which is 4.3 meganewton, a bit to the other side. So as I told you at the beginning, method of fragment is not very accurate, but it is an approximate method that can be calculated easy with the calculator. I hope this tutorial help you to understand how to calculate the seepage, the head loss, and the uplift force on a structure. Thank you very much for your time and see you in the next tutorial.